Okay, good morning, everyone. Welcome back. So this talk is following a set of great talks about radial velocity observations. As you probably are all too aware by now, there are a lot of problems that we have to overcome to get really precise radial velocity observations. And I guess I'm going to add a layer on that, but hopefully it'll be very useful for you. So just to remind you, to remind ourselves what the main goal of our endeavor here is, why are we so focused on getting all these super precise radial velocity observations? And that's because we want to measure precise and accurate masses for our planets so that we can characterize them. Okay, so as has been said several times, and Peter talked a little bit about it, stellar activity is really one of the, it's still that really big nail in Sharon's slide that we have to hit on, and we have to, it produces variations with amplitudes of several meters per second, even in the quietest stars. So the sun, which we think of as a really quiet star, even when it's quiet, the star spots and the faculae and all the magnetic features that come and go on the stellar surface produce radial velocity signals with an amplitude of about 1 meter to 2 meters per second. And we actually have solar data that shows that. But I'm not going to show you that today, but I just wanted to mention that. And so that's really one big barrier that we have to overcome. And as Peter was saying, we do have spectral activity indicators such as the Gaussian H and K. If you're looking at M dwarfs, you can use the H alpha. And these indicators do work to some extent. So they work on some stars, they work really well. But on some stars, they don't work well at all, or they don't work as well as we would like them to, for us to be able to disentangle stellar activity from the orbit, the reflex motion of a small planet. So I'm talking about a small Neptune, a super Earth-sized planet with maybe 5 to 10 Earth masses. And that's the bar I'm setting, but if you're looking for, Earth mass planets and 2 Earth masses, it becomes even trickier, right? So basically, we don't really understand stellar activity, and that's the premise of this talk today. And so this is what I've just said. So we don't understand stellar activity processes well enough that we can model them using physically driven models. And in this talk, I'm going to be when I talk about stellar activity, I talk more about the rotation modulated signals from star spots and faculae and active region groups on the stellar surface that are modulated by the rotation of the star and that come and go with time because they evolve. So I'm not talking so much about granulation noise from the for example, you can see here the granulation creates this sort of flicker of a few centimeters per second. I'm not talking about that. That's on very short time scales of a few minutes. And I'm not talking about magnetic cycles, which are in time scales of several years. So I'm talking about the time scales of the order of the rotation period, so a month, a few days, a few weeks, which is really what's stopping us right now. And we could actually give a whole talk about the physical processes behind this, but this is not today's focus because, well, we have plenty of problems to tackle. But this talk is going to be more about the solutions. So the thing is, we can't model stellar activity. I think I've said enough about that. But it's not because we can't model it that we shouldn't account for it, because if we know it's there, and if we don't account for it, we might get a really biased mass determination, right? And so, our mass determination would be inaccurate. So this is where we account for stellar activity as noise. And basically, by accounting for it as noise, we're going to be blowing up our error bar to a proportion that we think incorporates the uncertainty induced by stellar activity, by these unknown processes. Right, and moreover, so we've had already quite a bit about uncorrelated noise. So the jitter term that is added in quadrature, for example, I'm going to show that in a minute. But really, we know that the stellar activity processes are modulated by the rotation periods, and that come and go because the active regions are dynamic and they evolve and they change. So we know that this noise is correlated in nature. It's not uncorrelated. It has a time varying structure. So here's the outline of my talk. The first part, so I'm going to talk a little bit about accuracy and precision and signal and noise and correlated and uncorrelated noise. And Tom Laredo yesterday talked about this, and I just wanted to drill it in because they seem like really basic concepts, and I guess they are, but they have statistical and philosophical implications that it can be really useful to think about them for us to determine precise and accurate masses for our planet. And then in the middle of my talk, I'm going to give a brief introduction to Gaussian processes. So for those of you who are really excited about finding out about Gaussian processes, it's going to be a brief intro. For those of you who really don't want to hear about Gaussian processes, it's just going to be some more talk about correlated noise, so you don't have to worry about anything. And also, for the record, I'm not a statistician, and actually I get really worried about statistics, and I'm not statistically minded, and really the aim of this talk is to give you a more intuitive grasp and understanding of what's going on. All right. And so what I'm going to do also is spend some time talking about how, because we have a statistical tool like Gaussian processes, we want to think about what we're trying to account for and how we can, even though we don't know everything about what the star is doing, maybe we know a few things that can help us tailor that noise framework to the problem and get a more accurate and precise map. Right, and I've stuffed this talk with references and reading at the end. So if you have any questions, feel free to come and talk to me or ask me at the end. But you can also go back, and there are tutorials, there are talks, there are books, there are papers, there's everything. Right, so let's start with a very simple example. We have, say, I've decided this would be a mass radius diagram because we love mass radius diagrams for planets. And these are two measurements. Well, so they're the same planet with the same parameters, but what we've done is for the blue point, we basically we used a given model and a given framework, and we analyzed the radius, the transit data and the radial velocity data, and we got a given mass and radius, and we've got error bars here. And for the same planet here, we applied a different model, a different technique, and we got a different answer. So with that information, which one do you like best? Is it, who likes the blue one best? Who thinks this is the better one? Who's for the red one? Who doesn't have, who thinks there's not enough information on this graph? All right, okay, yes. So you actually need to know what the true value is, right? Otherwise, they don't mean anything. And so if the true value, if your planet is actually at this given mass and this given radius, then this blue point is the better one. Do we all agree? Yeah. So that red one, it's really precise, but it's completely inaccurate. Okay, and it took me a long time to understand that. This is why I'm showing it to you today. And in comparison, this blue point, it's comparatively less precise, but at least it's accurate, right? And so most likely what happened with this red point, the model is either our model was incomplete. So say that this planet goes around a star that's really active, and the transit measurements were completely messed up because you had loads of spots on the stellar surface, and you had these occulted spots and unocculted spots. And so we got a completely wrong, well, we got a different radius, and but we didn't account for those spots, so we got a really small error bar, right? And for the mass, it could be the same thing. So the radial velocity variations were really affected by stellar variation. And we also get, but we didn't account for that. So maybe in this analysis, we didn't even account for jitter terms, so like uncorrelated noise. And we definitely didn't account for correlated noise. So we get this really small error bar. So that's usually what happens when you get, that's one way to get a really precise answer, basically, but it's not the correct way. Right, so ideally, our goal is to get both, right? We want to get an accurate answer that is also precise at the same time. And so this brings me to signal and noise, and this is very basic, but again, it took me a long time to understand this, so I'm passing this on today. So any value obtained by an observation, so for example, RV, contains two components. So first, you have signal. That carries the information of interest. So for example, the planet's reflex motion. So this is basically, this is our interpretation of what is in the observation. So there are two things, signal and noise. And signal is the part that we know about and that we care about, okay? But then second, there's everything that we don't know about and that we usually don't care about either. And so that's what we call noise, right? And so noise basically encompasses all the unknown processes that we do not understand. And stellar activity at the moment falls into that category mostly, except if we have really good correlations with, say, the calcination K. We're really lucky, we can correct the activity by modeling it. But quite often, we end up having to treat stellar activity as noise. And that's better than ignoring stellar activity if we know it's there. And so the noise can either be random, so that's the uncorrelated noise, or it can be correlated. And the way we account for signals is that we model them. So for example, that reflex motion from the planet's presence around the star, we account for using a Keplerian. And the way we account for noise is basically through the error bars, and that is determined in our goodness of fit, so the chi-square or the likelihood. So the chi-square and the likelihood. So Tom Laredo talked about this yesterday. I'm just going to glaze over it briefly. Basically, if you have no noise, you can write out a chi-square, which is a goodness of fit. You want to minimize your chi-square to get your best fit. And the chi-square looks like data minus model squared divided by error bar squared. That's what we saw yesterday. And you can extend that to include uncorrelated noise. So noise that is random, that is Gaussian distributed, that we call white noise because it's wavelength independent. I think that's an old term that we are moving away from. And we call it jitter as well. So this is typically a constant that you can add in quadrature to your error bar. Right. And in those two frameworks, the likelihood is just the exponential of minus chi-square over 2. Right. So the two have a very simple relationship to each other. Now, in the case of correlated noise, so basically non-random noise that has a structure that is not Gaussian distributed, this relationship with the likelihood and the chi-square breaks down. And so you can't write that the likelihood is equal to this. And as it happens, there's a covariance matrix involved, and I'm going to show you that in the next few slides to hopefully give you an understanding of what's going on. But basically, this is not correct because this is not correct. Right. It's the rest of my talk, so it's okay. Right. Yes, so now I'm going to start with the uncorrelated noise. And so, as I said, it's random Gaussian distributed data. I've taken some observations, and these are fake, but this is, say, a time series of radial velocities, and I've got 200 points there, and your eye is looking for patterns, but I promise, this is random Gaussian distributed noise. And there's nothing else in it. And you've got the error bars as well. And so now, if I look at the correlation, the amount of covariance between each of those points, so say I take this point, and I say, okay, how is it correlated with that point, and every other point? And how all of these points correlated with each other? Are they correlated with each other? So I see lots of no's. Great. Yes, they're not correlated with each other by construction. And we can encode all that information in the covariance matrix. So basically, here are the 200 points again, and the 200 points at the top. And just to make this completely clear, this is a simplified cartoon of what's going on here. Basically, you have the covariance of every point with every other point in every entry in that matrix. But that's a 200 by 200 matrix that looks a bit messy, and it's real data. So, but basically, what you're meant to see here is that it's just a diagonal matrix. So everything in the off diagonal element is effectively 0. So the covariance, the correlation is 0. But in the diagonal, the correlation is non-zero. And that is because the diagonal elements are basically the correlation of one point with itself. And that's just the variance. And the variance is just the error bar of the data point, right? Does that make sense? Okay, so this is basically the simple case, and that's why when you have uncorrelated noise, you can simplify your likelihood down to the chi-square, because basically in the likelihood you have the determinant of that matrix and the determinant of an identity matrix, so one where there's just diagonal elements, simplifies down to one single value. So that was uncorrelated noise. Now let's look at noise that has correlation in it. So this is, I've got Gaussian distributed noise in it, but there's also something that is correlated, right? And actually it's recurring, it's a recurring pattern. So this is now what the correlation, the covariance matrix looks like. And so again, you have the diagonal elements. And what you see is that there is a little bit more structure in the covariance matrix. I hope you can see it, actually. Okay, this didn't come out too well, but here's the cartoon. So, so the diagonal elements, and then you've got no covariance, and then you've got covariance again, because by the time, so if you take this point, for example, you don't really know what's happening here, but you know there's a degree of correlation in there that says, oh, but a time t later, we're going to be back in the same space. And actually, so if you look at the periodicity that's in this plot, you can see it also in the covariance matrix. So if you look at so it's a periodicity of about 60 days, and you can see that if you go in this direction, you've got 60 days, right? And it continues. So you have this sort of symmetric pattern about the diagonal. Okay, so the covariance matrix is a way to encode the correlation between all the observations. Okay, so now let's move on to some real data. This is a light curve from Perils 7, which is my favorite star. A star I worked on for half my PhD, so my favorite in most cases. But it's an active star, and this is the light curve from the second run. So the Corot spacecraft, Corot 7 was initially, Corot 7b was initially detected, and people got really excited because at the time that was the smallest planet we'd ever found. It was 1.5 Earth radius. And then we discovered that actually the star is really active, and people took lots of radial velocity observations, and they went and did their analyses, and they got completely different masses because of the activity. So they got inaccurate measurements, and they were not accounting for activity because they didn't realize that they had to back then. That was in 2009. So anyway, so then Coro went back and looked at the star again, and this is the light curve it got over about 80 days. And you can see the variations here. They're all due to dark spots coming in and out of view as the star rotates. So I was going to show you the, basically you can find that the rotation period is about 23 days. And you can see that from one rotation to the next, you get differences. And that's because the active regions on the star surface evolve over time. So they change shape, they change phase, they disappear, they come back. So you have this quasi-periodic type of noise, right? And so this is the covariance matrix that you get. So you still see the diagonal elements, but you see definitely a lot more structure in the off-diagonal elements because each point is correlated with another point that is not necessarily just one rotation period later, but in between. But at the same time, the active regions evolve, so it's not completely correlated. There is some evolution. That's a simplified version. But hopefully by now you're used to looking at that. So, right, and so again, this is the rotation period, and you can see that you have, so it's not super apparent in this plot, but you could see it in the cartoon. So you have the diagonal element, and then one rotation later, you'd have another peak, but it wouldn't be at quite the same amplitude. So you have a little bit less covariance because of the evolution. And then again, if you look one rotation later, again, you see the same thing. You see this periodicity, but that's being blurred out. So basically the essence of Gaussian processes and any correlated noise framework is instead of fitting this light curve with a parametric model, you fit the correlations in the covariance matrix. Okay, and you can do that by approximating. So you choose a covariance function in order to fill every element. So here's the covariance function. This is one that would be appropriate to, that we could deem appropriate to fit in order to fill the covariance matrix. So basically, I'm going to talk about it in a bit, but you see that you have this recurrence, and you see that you have a decay over time, right? I'm going to come back to that. And the thing about this is that you can write out an explicit form for it, okay? And what you can do is instead of fitting the data, so instead of fitting that light curve with some very complicated model, and you probably need, I'm just going to go back. You would probably need many different sine curves at many different periods to fit this. This would be really complicated, right? So instead, by fitting in correlation space effectively, we just have this one equation. And when we do that, so this is the observed covariance matrix, but if instead I choose some values for my hyperparameters, and I calculate each covariance at each point, I get this. So it's an approximation, but you can basically see that you have the diagonal elements again, and the points that are very close to each other are very correlated with each other, as we would usually expect in nature. And then the correlation goes away, but then when you hit the rotation period again, one rotation later, you might have some active regions that, although they've evolved, so this doesn't look as dark as that, they're still there. So you still have some level of correlation, of resemblance. Okay, and just to maybe give you a sort of proof of concept, I'm now going to use this covariance matrix that I'm filling with this function to create some light curves that look just like the Coro 7 one. So here's one. So does anybody see a difference with the the actual Coral 7 light curve, it looks very similar at first glance, right? And that's because the frequency structure is preserved. And that's the whole point of the covariance function, right? But then you do have some flexibility. So here's another example. So again, you have the same sort of recurrence every 23 days at the rotation period, and you have an evolution. So it does change, but overall, you see the same kind of structure. And so these three light curves, I'm going to go through them again. They have the same covariance properties. Right. So that was a very brief intro to Gaussian processes. I hope you're still with me a little bit. I only had 40 minutes. So, but now I'm going to go back to step back and think about, okay, so we have this very strong statistical tool with which we could account for stellar activity variation. And by accounting for them, we can get error bars on our mass determinations, which are more realistic and which acknowledge the fact that we don't know about all this noise, but we do need to incorporate it because it will bias our mass determination. And so what can we do with this covariance function, with this tool to account for stellar activity? What can we do to maybe physically motivate it a little bit more? And basically, I'm going to talk about why this particular form of covariance function, so you probably got a feel for it in the previous slides, why this function is adequate, because it's quasi-periodic, basically. So let's go through it in a little bit more detail. So that's the only equation. Don't worry, I'm going to talk you through it. So that's just the amplitude. It's an amplitude term for your covariance. And there you have, so I'm going to start with this term in the exponential. So you see this has a sine term. So that's the periodic component. And it basically tells you about the recurrence of the signal. Okay, so how coherent it is. And that's basically the rotation period of your star. So we found that it's adequate to basically just say, I'm going to take this parameter and I'm going to learn the rotation period of my star with a different data set. So for example, that light curve gave the rotation period. And I can basically use that value for this parameter. The next one that I want to talk about is this term. So this is an exponential decay. And this is actually pretty well, physically speaking, this corresponds to the evolution of the active region on the stellar disk, right? And we can actually measure this. So Helen Giles, here with us today, did some a great analysis. She took a bunch of Kepler light curves and she looked at the variations of thousands of FGKM stars, and she actually deduced the active region lifetime of these stars. And there's actually an equation in the paper, so you can, and you have plots, so you can go and get an idea. So say you have a G-type star, what kind of evolution lifetime would you expect? And she found that in particular, F stars don't have a lot of spots and they don't live for very long. So there aren't too many big spots. The bigger spots live longer. And that's because the spots decay by the granulation cells around them that eat them up. So you can basically now get an idea of what the evolution timescale for your active region could be on your star. So you can get a value for this number, this decay timescale. And then I would like to talk a little bit more about this last parameter, which is maybe a little bit more elusive. We call it the structure parameter. And it basically dictates the shape of this. So yes, as my arrow points, the covariance goes to 0 in those times, because that's basically when the active region that you're sort of thinking about goes around the back of the star, so you can't see it. So because you can't see it, you don't know anything about it. But because we have this covariance function, we can predict to some level when it comes back and how much it will have evolved. So that structure parameter tells you a little bit about this and about what the shape of the function should be around those edges. So it tells you about the high frequency structure of the covariance function. And I have a few slides about this. So for those of you not interested in Gaussian processes, this is actually totally relevant because this is really about degeneracies, and Jennifer is going to talk about it more this afternoon. But I find this really enlightening to go through this. So basically, the idea is that in a light curve, you're only ever going to get 2 peaks per rotation because of all the degeneracies involved. And I'm going to show you that. And in the radial velocity curve, it's the same. The radial velocities are a little bit more complex, so maybe you can get 3 peaks per rotation, but you can never get 10 peaks per rotation. So you can never get that amount of complexity. And so Sandra Jeffers did a great little paper. This is like a 4-page cool star proceeding, where she created these synthetic stars, stellar surfaces, and she just chose any kind of spot configuration that you can imagine. So now just imagine whatever spot configuration you want and put it there. And then what she did is that she took this and computed what the light curve would be. And this light curve is face folded over the rotation period. Okay, and you see 2 peaks. But here is where it gets really, really cool and really sad at the same time. But then she took this light curve and she decided to do the reverse step. So from this light curve, she recreated the stellar surface again. And that's what she gets. So this is a map. So it's a longitudinal map. But basically, it's just the star sort of laid out flat. And this looks very different, right? You only get 2 spots. And what she found is that no matter what the configuration here, she always gets this because of the levels of degeneracies involved. So basically what's happening is that all of these spots on this side of the star, they're kind of averaging out into one big spot. And then on the other side of the star, the spots are doing the same thing. They average into one big spot. And then as the star rotates, you just see the difference between these 2 spots. And that just looks like 2 spots. So because of this level of degeneracy, we can constrain this final parameter, the smoothing parameter that gives you the structure, especially the high frequency structure in your light curve, to how much structure you're going to have per rotation period. A bit like this, so it can't be squiggly. You can only have like 2 peaks. And that corresponds to a value of about 1/2. So you can basically constrain that really easily with those kinds of degeneracy arguments. And that can help you physically motivate your Gaussian process and your covariance function. Okay. Right, so this is it for this slide. I'm going to say a little bit about, for those of you who are interested in Gaussian processes, how we can use them to account for stellar activity variations in radial velocity data. If you've had too much, just glaze over for a minute. But basically, the idea is that we want to determine these 3 parameters, and so we can either we can either fix them. So as I've said, I've given you arguments for why you might be able to go and look at different data, ancillary data, and say, okay, I can measure the rotation period of this star. I can measure the active region lifetime. I know that the smoothing parameter should be about 0.5, and I can impose really strong priors on these parameters. And you would fit these parameters as part of, say, an MCMC. in your overall radial velocity code. But you could also use ancillary data sets, for example, the light curve or the calcium H and K if you had a good cadence, and you could use them to constrain the values that these hyperparameters should have if you wanted to maybe let the data speak more for itself. So there are many different ways, basically, that you can play with this covariance function. But if you have any questions about this, come and speak to me afterwards. We can talk about it, or look at the tons of references at the end. Right, so the last thing I want to talk about, which I suspect is going to come up in the questions if I don't talk about it. So, will the Gaussian process eat my planet in my radial velocity data? And the short answer is no. So that's good, but it is worrisome because basically the Gaussian process is this really flexible thing, and it can incorporate, it can absorb lots of signal, lots of noise, if your model does not already have something in it that will better model that signal. And so here is an example. This is work that I did actually with the Coral 7 data set. We had a planet in there, Coral 7b, which is actually the second harmonic of the rotation period. So we think that is not a planet. But basically, we have a data set. And in here, this is a fake data set. So I injected uncorrelated noise, and you can see I put a Keplerian in there. And my framework, basically my model, I had a Keplerian in my model, which is here. Oops. Sorry. I had a Keplerian, and I also had a Gaussian process that is incorporated in the equation for the likelihood. Again, we can talk about it afterwards. That has a quasi-periodic covariance function, and it's the quasi-periodic covariance function incorporates it has the same frequency. It has a frequency structure that would allow you to eat that. Okay. Basically, the Gaussian process is very flexible, and if you had no model, no Keplerian, the Gaussian process would have no trouble eating all of that and giving you that residual. Okay. But because we have this Keplerian in there, the Keplerian absorbs all of the signal. And that's because that's basically Occam's razor. So the idea is that the Keplerian is a simple, non-complex model. And the likelihood function, which is trying to give the right balance between the Gaussian process, which is very flexible and can basically eat anything, and this Keplerian signal, this Keplerian model, the likelihood is going to penalize the more complex things, and the Gaussian process is more complex. Whereas, so it can absorb it, but because there's a Keplerian in our model, the Keplerian is going to be favored because it's simpler. Does that make sense? Right. And so with that Occam's razor sort of naturally built into the likelihood function, we are less worried that the Gaussian process is going to absorb the planet signal if it's there. But that's only if we include the planet, if we include a Keplerian model in the model. Right? If we don't, then we're not going to find it. Right, so here are my conclusions, just to finish up. So the aim that we all want to have is to get precise and accurate planet masses. But really, if we have to choose between one or the other, I would go for accurate. And precision is going to come when we have a better understanding of stellar activity, a better physical understanding of what's happening on the surfaces of these stars to these magnetic fields, how it creates those radial velocity variations. And if we sample the observations over the rotation and evolution timescales of the stellar activity, then with that sampling and with those activity models, we'll be able to get a precise answer. But for now, we can use a Gaussian process to obtain at least an accurate answer. So the I skipped a few bullet points there. But basically, the Gaussian process it's not the final answer because it's not a model. It's never going to do as good a job as a model, but it will give you an answer. It gives you a way to incorporate the uncertainties. So the fact that we don't know what activity is doing, and so usually it blows up the error bar to give us that more accurate answer. Yeah, and the final point I want to make is that the statistics, so statistical tools like Gaussian processes and any other correlated noise framework, they're really useful and you should really go for them. But they're not going to tell you, they're only going to tell you about the statistical significance of a signal. They're never going to say, oh, it's a planet, it's stellar activity, it's an instrumental. That's what we as astrophysicists have to do. And so you have to remember that basically statistics is not magic and it doesn't solve that kind of problem for you, but it can tell you with what significance you detected a thing. Okay, so I'm going to stop there. Yeah, it's probably, well, I mean, you have to sample your planet signal because if you don't sample your planet signal, you're not going to see it. It does, I mean, well, all the work I do is with transiting planets. So we already know the orbital period and the phase of transit. So we know we can put these constraints in our radial velocity analyses. But if you don't have that, it gets a lot more difficult. Yeah. So the Gaussian process will basically, well, what I think is actually a great advantage about stellar activity, the fact that it's not coherent and not periodic, that's one big difference between a planet signal that is coherent and periodic always. And so that can also play in. Yeah, great question. So how do you know that the GP is not affecting your mass determination of your planet? And so that's especially true if you say have a system where the rotation period is very close to or the first harmonic or the second harmonic, so half the rotation period is close to your orbital period of your planet. And then you have a GP and a Keplerian competing to absorb those signals. So there will be a coherent part, which is that of the planet, but maybe some of the stellar activity is going to be coherent as well. And so maybe you're going to be overestimating your planet signal because the Keplerian takes everything that's coherent and the Gaussian process takes what's not coherent, but maybe that's not all of the stellar activity. And so then you might be biasing the results as well. So that's really what I'm saying. We still need to think about what we're actually doing. We can't just take the answer of the GP for granted and not think about it again. Yeah, so the question is basically, how do you know where to initialize the GP? So parameter values you want to give in your covariance function, basically. And that's, yeah, I think that's where we need to be really careful, and that's where we can really turn the GP into something that will give us a more accurate answer. Or if we're not careful, then we might end up the error bar might still, I mean, at the end of the day, we're choosing the error bar really. And so we're choosing it by choosing those parameters. So yeah, I mean, the few slides I had about choosing the rotation period and all of that were just to get you thinking about doing stuff like that. But yeah, I mean, you might want to talk to someone who measures rotation periods of stars. This is very fun, because then you branch out into all kinds of different fields, right? You go more into stellar activity, and you might want to study the stars themselves a little bit more, and determining rotation periods, as you've mentioned, you can do it with a periodogram. There are other techniques. So for example, Helen uses an autocorrelation function, which can help you find, sometimes it works better at finding the true rotation period and not half. But these are basically all details that for which I would encourage you to think about, and to then go and, if you don't know the answer, that's fine. Go and find someone who might have something more to say about it. And that's how you can maybe put some more physics into something that is very statistical based. Does that answer your question?
I don't think you said anything about how one would fold in measurements of the spectroscopic activity.
Yeah, so how might you fold in measurements of the spectroscopic indicators, so like the calcimation K? Great question. So I would say that would fall more in the side of the model. So I would argue that you could have both. You could say, okay, I have these calcimation K measurements. I know what the relationship between the RV and the calcium H and K is, so I can create a model, even if it's like, you know, alpha times calcium H and K. But that's a model, and maybe it only works to first order. So maybe you're going to apply your model, and you're going to find lots of correlated residuals with a frequency structure that you have, it's modulated by the rotation period, and it has this evolution. And that, what's left, you could account for it with a Gaussian process. I would like to think that you would get a more precise answer doing that, because you're incorporating a little bit of physics, right?